We're moving on to a new territory. Okay. Before we move on, as reminded by our wonderful TA, I think it's very nice to let you know the comparisons, the differences between the E field and the B field. So this one is called Gauss's law, right? If you still remember, we also covered Gauss's law and we calculated the E field intensity pattern by invoking Gauss's law. Now, we also introduced the Ampere's current law, circuital law, right? And we just showed you two different examples. But if you think back, whenever you want to invoke Gauss's law, I particularly mentioned your given problem has to show certain type of simplicity in terms of geometrical symmetry, or you have very uniform charge density. Otherwise, you have to use the Coulomb's law, right? Coulomb's law is a tool where you don't have full insight to your problem. You only know your charge distribution, charge density distribution, and you just sum it up over the entire volume, right? So in direct comparison, when we march into the fields of magnetic vector fields, even though we have a very simple rule taught by Ampere, if you have some current density, ideally you would produce magnetic fields. But this equation, as I just showed you previously, if you want to use it, you also need to have very deep understanding to the problem you're trying to investigate. You have to have some impractical assumption of infinity length, uniform current distribution, geometrical symmetries, right? So then the question now is, well, if the current density is not a constant, your geometry is not symmetric, do we have also a tool like the Coulomb's law for electricity that can permit a straightforward calculation of the resulting B? All right, so that's the entire purpose for the following 15 minutes, right? Again, using Gauss's law for electricity, Ampere's law for magnetism requires your deep understanding. If you don't have the confidence to invoke these two laws, well, we want to have direct, messy, but brutal force integrations. So luckily, in electric fields, we have Coulomb's law. But up to now, in magnetic fields, we don't know how to do it, right? And that's the entire purpose, the meaning of introducing a vector magnetic potential, right? The definition comes from vector null identity. Well, if you still remember, if you have some vector field and you take its curl, it's not equal to 0, then your resulting, after the curl operation, you're trying to find the circulation, right? And therefore, if you have circulating field, the field closes upon itself. Then you take its divergence, it must be 0, right? This is the meaning behind this null vector identity. But coming from our basic postulate, when B fields are vortex fields, all the B field lines close upon themselves. Therefore, divergence of B equals to 0. And the physical meaning is we cannot easily find an isolated basic element to produce B fields, right? You don't have an isolated independent source. But if we compare these two equations, well, can we say that because the B field is a non-conserved vortex field, so its divergence is always equal to 0, but at the same time, we know the null identity divergence of a given vector is equal to 0, then this vector field itself can be defined as the curl of another vector field. So what about this? Now basically, B, our magnetic flux density, can be defined as the curl of another vector field. And this vector field we define as our vector magnetic potential. So up to now, everything is just mathematical. So later on, I'm going to show you the physical meaning of A, and I want to show you by introducing this new quantity actually allows us to finish the task with a new law, so that even though your current density is non-uniform, but it allows you to directly integrate to the B. Okay? So basically, if you have current density as a function of space, how to get B? And defining this vector magnetic potential A satisfies our need. Okay? Right? So now we have defined a new vector quantity. So basically, everything you need to understand about magnetic fields are right in front of you, right? You have current density. If you have currents, you can produce magnetic fields, right? Eventually, we want to know B, but even though Ampere's circuitous law is very simple and straightforward, but it's not very useful every time, okay? So this equation is indeed true, but even though you have some known current density, you don't have a direct and easy way to know B. So we introduce A, okay? So up to now, comparison between E and B, E fields are conserved, and we have defined an electrical potential, which is scalar. In the same analogy, we also defined a potential in magnetic field, but it is a vector. And B and A are related through a curl operation. So how to perform curl is extremely crucial, right? In order to master magnetic fields, you have to have the capability to perform curl operations. All right? Physical meaning of vector potential A. So assume I have some area, right? I have magnetic field lines penetrating across this area. And we can just draw a circle, right? And we have the magnetic fields coming from our Earth. Our Earth is a big magnet, so we can have fields penetrating across this area. So the area is S. Around it, the circumference is a closed loop C. So if we ask ourselves, well, if I want to evaluate the total number of magnetic field lines penetrating this surface, how should I do it? Simple and straightforward, right? This is called the flux, magnetic flux. The amount of field lines crossing the surface is called the magnetic flux. I only have to perform the surface integration of B, right? And therefore, B is called the flux density. if you perform the surface integration, that gives you the flux. But now that we know, through our definition, B is equal to curl of A. Well, that's following from vector null identity, curl of A. So if you have a surface integration of the curl of a vector field, that is reduced to the closed loop line integration of that vector itself. Again, this is using Stokes' theorem. And that's the reason why we covered divergence theorem, Stokes' theorem up front. Okay? So now what you can see is, if we care about the magnetic flux, we actually have two ways to calculate it. One is, I want to know phi B, I can perform the surface integration of B, or equivalently, I can calculate the closed loop line integration of A. So the meaning of vector magnetic potential A is, you can get the same magnetic flux just by performing a line integration along a closed loop at the outer edges of your surface. Okay? So the physical meaning is apparent. By defining A, you can reduce your integration by one order. Surface down to line. Right? So ideally, we're hoping, well, even though we have introduced a new term, but because the calculation involved is having one order of reduction, one dimension of reduction, so we might be able to find A directly from J. And then I perform curl of A to find B. Right? So this is telling you, if the mountain is not turning, the road should turn. 山不转路转. Okay? It's very difficult to find B from J. Let's give up. Let's try to reroute. Let's find A first, and then from the definition, curl of A gives B. We take the indirect path. Okay? So again, the need to define A is, even though the Ampere's circuital law is coined here, but if you have the J known, curl operation of B equals to that, you don't have a direct way to find B. Okay? So we're hoping to introduce a new field quantity of A that could help us to land in B in a direct way with known J. Okay? But if you are a very strict person in terms of mathematics understanding, you would find, well, this definition is incomplete. Why? Because we have defined the vector magnetic potential A, the curl of it is equal to B, right? Our magnetic flux density. But if you want to have a well-defined vector field with a known curl value, it's only 50%. The other 50%, to have a well-defined vector field, comes down to the requirement, you also have to know the divergence of that vector field. Right? So this is a simple mathematical issue. How should we define the divergence of A? Well, the divergence of A is really arbitrary. Because in the end, think about it. When we deal with math, we have to have a well-defined divergence of A and curl of A to have a well-defined vector field. But in the end, do we really care about the divergence of A? All we care about is curl of A, right? Because B is equal to curl of A. So essentially, what is the quantity of divergence of A is not that important, right? So we are free to assume whatever value divergence of A is. Okay, that's our freedom. But to be complete, we still have to define divergence of A to something. So in principle, although it's arbitrary, but we still want to define it so that A is completely defined vector quantity. So in reality, we like to have divergence of A equal to 0. Why? Because we're lazy. Something equal to 0 is simple and straightforward. Is that the whole reason? Oh, it's not because we're lazy. Think about it. Ampere's circuital law tells you this, okay? And B equals curl of A. Does any one of you still remember the operation of double curl? We actually covered this. If you have a vector quantity and you perform double curl operation, that is equal to, this is actually the definition of the vector Laplacian, right? Divergence and then the gradient of the vector field minus the vector Laplacian. Okay. So now can you see why we like to define divergence of A equal to 0? Because we don't have to deal with the first term. This assumption is called the Coulomb's gauge. Okay? So even though divergence of A can take on any value, but if you specify to 0, it's called Coulomb's gauge. That helps us to find a direct path. Now think you're Columbus. You're trying to discover the new world. You're trying to discover India, but somehow you found America. Okay? So initially, from J, we want to land in B, but somehow we find it too difficult. We introduced A, and then we defined divergence of A equals to 0, so we don't need to solve. We don't have to care about this term. So magically, it seems it's possible that if I know J, I can land in A directly, right? So this is Columbus, and this is India, but this is North America. Beautiful. Okay? So let's come to this equation. Under the assumption of Coulomb's gauge, divergence of A equal to 0, we only have to solve Laplacian A equals to negative mu 0 J. So now, you have to think, this is really a major step forward. Why? Laplacian, how? What is Laplacian? Laplacian in Cartesian coordinate is just double differentiation, right? Double differentiation as compared to curl is still easy and straightforward. So now, by defining this A, it seems we have the potential to acquire A directly from J. We don't like curl operation, period. All this effort, we want to remove the curl operator. Right? So in Cartesian coordinate, Laplacian is for each component having its scalar Laplacian. Right? But it's still straightforward because scalar Laplacian is that component having double differentiation in all directions. Still manageable. Okay? Now, you might be puzzled. Well, after you perform the Laplacian of A, you still have a vector. Right? You still have a vector. You still have an x component, y component, z component. So that is equal to J. J itself is a vector. So even though you have 9 terms, 3, 6, 9, you have 9 terms, but you can group the results into 3 terms, right? By directions. In the x direction, y direction, z direction. So therefore, you come up with a set of 3 equations. So this is telling you, again, a lot of information. Your current density flowing in the x direction directly associates to the x component of your vector magnetic potential. Okay? And the y current density component directly determines AY, JZ, AC. Right? So now the question is reduced to a set of 3 scalar Laplacian equations. That should be doable.